US Physics Olympiad, year 2019, first round, F = MA, exam B. This year exam was split by two flows, exam A and exam B, and the students could participate in any of them. For exam there were, as usual, 24 problems, and that was given 75 minutes for this amount of problems. If you want to get more interesting problems in physics, just subscribe for this channel. Problem number 1. A uniform block of mass 10 kg is released at rest from the top of an incline of length 10 meters and the inclination 30 degrees. The coefficients of static and kinetic friction between the incline and the block are mu static equal 1.15 and mu kinematic equal 1.1. The end of the incline is connected to a frictionless horizontal surface. After a long time, how much energy is dissipated due to friction? Solution for problem number 1. Because inclination 30 degrees greater than critical angle, it means that tangent 30 degrees greater than mu static, there will be motion on this incline, and all energy dissipated due to friction, it's because of work done by force of friction. And this we can count using a regular formula. Work of force of friction equal force of friction multiplied by distance, which is mu kinematic mg cosine theta multiplied by L. After putting numbers, we will get 87 joules. This is answer B, and this is the solution for problem number 1. Problem number 2. 3 cubical blocks of the same volume are made out of wood, styrofoam, and plastic. When the plastic block is placed in water, half of its volume is submerged. If the wooden block is placed in water with the plastic block on top, the wooden block is just fully submerged. Similarly, if the styrofoam block is placed in oil with the plastic block on top, the styrofoam block is just fully submerged. The density of oil is 0.7 times that of the water. What is the ratio of the density of wood to the density of styrofoam? Solution for problem number 2. First, let's say raw water equal 1. It means that raw oil equal 0.7. When the plastic block is placed in water, half of its volume is submerged. We can write equation volume V multiplied by raw plastic equal 1/2 volume V multiplied by raw water. It means that raw plastic equal 0.5. If the wooden block is placed in water with the plastic block on top, the wooden block is just fully submerged. We can write equation volume V multiplied by raw wood plus volume V multiplied by raw plastic equal volume V multiplied by raw water. Here we know what is raw water and raw plastic, and the raw wood equal 0.5. If the styrofoam block is placed in oil with the plastic block on top, the styrofoam block is just fully submerged. We can write equation volume V multiplied by raw styrofoam plus volume V multiplied by raw plastic equal volume V multiplied by raw oil. Here we know what is raw oil and raw plastic, and we can find what is raw styrofoam. That will be 0.2. And now we can count what is raw wood over raw styrofoam. That will be 2.5, which is answer A, and that was a solution for problem number 2. Problem number 3. Two springs of a spring constant K1 and K2 respectively are connected in series and stretched as shown below. What is the ratio of their potential energies? U1 over U2. Solution for problem number 3. First, we can write the equation for force F. That's equal to K1 x1 plus K2 x2, where x1 and x2, that's the extension for the first and second strings. Second, we can write equations for potential energies. U1 equal 1/2 K1 x1 square and U2 equal 1/2 K2 x2 square. And now we can write relation between these energies. That will be this expression, and after simplification, because K1 x1 equal K2 x2, we have finally it's equal to K2 over K1, which is answer C, and this is the solution for problem number 3. Problem number 4. Consider two identical masses that interact only by gravitational attraction to each other. If one mass is fixed in place and the other is released from rest, then the two masses collide in time t. If both masses are released from rest, they collide in time which one? Solution for problem number 4. Let's check the first case. Suppose that the distance between two masses is r, and let's count what is the time to cover distance small dr for the one mass. That will be delta t1 equal dr over v1, where dr is distance covered by one mass, and the v1 is the speed of this mass in this particular point. In other case, when both masses are not fixed, they share the same change of potential energy. It means that each mass has a speed v2 equal v1 over square root from 2 on the same distance r between these two masses, but the relative speed will be twice greater. It means that time to cover for both masses same distance dr will be this one, delta t2 equal dr over square root from 2 v1. Now to count what is the total time for the first case and for the second case, we can do integral. That will be this expression, and for the second case we have other integral, t2 equal this expression, which is squared from 2 times less than t1. So it means that in second case we have time t over square root 2, and that was answer D, and that was solution for problem number 4. Problem number 5. The density of the Earth increases gradually from around 3 gram per cubic centimeter at the crust to above 13 gram per cubic centimeter at the core. Which one of these plots could show local gravitational acceleration as a function of distance from Earth's center? Solution for problem number 5. The gravitational acceleration is 0 at the center of the Earth by symmetry. So it means that choices A and D are wrong. If the density is constant, acceleration is proportional to r. That's a well-known fact. It could be proved very easily. This means that choice B is for a constant density planet. But in case of Earth, density decreases with the r. We know that mass m growing more slowly. It means that acceleration must grow more slowly than linearly and may even decrease. So it means that choice C is not our case. It means that only case E is possible. That was a solution for problem number 5. Problem number 6. A very long cylinder of dust is spinning about its axis with angular velocity omega at steady state. Let r be the distance from the axis. If the dust is only held together by gravity, the density of the dust is proportional to which one? Solution for problem number 6. By Gauss's law for gravity, the gravitational acceleration at the cylindrical Gauss surface is proportional to lambda over r, where lambda is a linear mass density. The required centripetal acceleration is a equal omega square r and proportional to r. Hence we must have lambda proportional to r square, which is achieved if ρ does not depend on r. As in this case, lambda equal pi r square ρ. It means that answer is C, and that was a solution for problem number 6. Problem number 7. A trough half filled with water is suspended from wires as shown. The tension is initially the same in each wire. The boat is placed in the trough directly under the left wire. It floats without touching the sides of the trough or overflowing the water. How does the tension in the wires change as a result? Solution for problem number 7. The boat doesn't touch the wires or the trough, it only touches the water. The pressure at the bottom of the water remains the same everywhere, whether the boat is over top or not, because if the pressure were unequal, it would cause water to flow, but the situation is static. Therefore, the force from the water is distributed evenly over the trough and the tension is the same in each wire. The wires do support the boat through water system, which got heavier, so the tension in the wires increases. The answer is B, and that was solution for problem number 7. Problem number 8. The scale is calibrated so that it gives a correct reading when sitting on the ground. A person holds the scale and presses it on bottom sides with their hands, pushing up on the bottom with the left hand and pushing down on the top with the right. The scale has a mass of 5 kg, and their left hand exerts a force of 200 Newton. The reading of the scale is next one. Solution for problem number 8. Because scales in this student hand is in equilibrium, we can write equilibrium equation: force on the bottom equal force on the top plus mg. Here we know what is bottom force and what is mg, and we can count what is top force, which is supposed to be scale reading. That will be 150 newtons or 15 kilograms, which is answer A, and that was solution for problem number 8. Problem number 9. The light board of length L is hinged to a vertical wall. A solid ball of weight G and radius R is held between the wall and the board by a force F applied perpendicular at the end of the board, as shown in the figure below. Both the wall and the board are frictionless. The angle between the board and the wall is 60 degrees. What is the magnitude of force F? Solution for problem number 9. First, let's draw the free body diagram. We have force F1 acting on this ball horizontally from wall, and the force F2 acting on this ball from board. It means that the same force F2 acting from the ball to this board. And when we count what is F2, we can count what is F. Let's count what is the force F2. In vertical direction, we have static equation. F2 multiplied by cosine 30 degrees must equalize weight of this ball, G. It means that force F2 equal G over cosine 30 degrees. And now let's count what is force F. Force F and force F2 create opposite torques on the board. We can write static equation for this torque on this board around this pivot. That will be F2 multiplied by radius R over tangent 30 degrees. That's a torque from force F2 acting from ball to this board. That's equal to torque F multiplied by L. And from here we can count what is force F. That will be this expression, and after all, that's 2 GR over L. That's answer B. That was solution for problem number 9. Problem number 10. A ball of mass small m rolls in a ball bolted on a cart. The ball and cart move together and have a combined mass mc as shown in the figure. Initially the cart moves to the right with the speed v0 with respect to the ground, while the ball is at rest with respect to the cart. The ball then slides down to the bottom of the ball. When it reaches the bottom of the ball, it moves with the velocity vb with respect to the cart. At this instant, how fast is the cart moving with respect to the ground? Solution for problem number 10. Here we can use momentum conservation because there are no friction between cart and the ground. So it means that initial momentum equal final momentum. And there will be equation. Initial momentum, which is small m plus mc multiplied by initial speed v0, must be equal to momentum of cart with the ball, which is mcv, plus momentum of this small ball, which is m multiplied by speed v plus relative speed vb. And from this equation we can immediately find what is speed v of this cart with the ball. That will be this expression, and this is answer D, which is a solution for problem number 10. Problem number 11. Consider a flat uniform square of mass m and the side length L. Cut a circle out of the square that has a diameter equal to the length of the side of the square, with the same center as the square. Determine the moment of inertia of the remaining shape about an axis through the center and perpendicular to the plane of the square. Solution for problem number 11. The moment of inertia of the square about a line that divides it into two equal rectangles is this one. By perpendicular axis theorem, moment of inertia of a square about an axis through the center of mass perpendicular to the plane is twice this, 1 over 6 ml square. Moment of inertia of the removed cycle is this one. It's 1/2 mass of this cycle multiplied by radius square, where radius is L over 2. So finally we have 1 over 8 mass of this cycle multiplied by L square. And the mass of this cycle is pi over 4 of this big mass of initial square. So finally we have moment of inertia of this cycle is pi over 32 ml square, and the moment of inertia for final figure is I2 minus I3, which is this expression. That's answer A. That was a solution for problem number 11. Problem number 12. Two planets A and B have masses ma equal to mb. They orbit a star in circular orbits of radius ra equal 3 rb. Let EI and the Li be the kinetic energy and the magnitude of the angular momentum of the planet I, respectively. Which of the following is true? Solution for problem number 12. Kinetic energy for any planet around star equal g mass of star mass of planet over 2r, which is proportional to m over r. Angular momentum of any planet equal mass of planet multiplied by square root from g mass of star multiplied by radius r, which is proportional to mass multiplied by square root from radius. It means that kinetic energy of planet A equal 2/3 kinetic energy of planet EB, which is less than EB, and angular momentum for planet A equal 2 multiplied by square root from 3 angular momentum of planet B, which is greater than angular momentum of planet B. So it means that the correct answer is C, and that was solution for problem number 12. Problem number 13. A water hose is at ground level against the base of a large wall. By aiming the hose at some angle and squirting water at speed v, one wets a region on the wall as shown below. If the speed of the water is doubled, what is the new region that can be wetted? Ignore the effect of water splashing beyond the point of contact. In the answer choices, the dotted line marks the initial wetted region. Solution for problem number 13. The only dimensionful quantities in the problem are speed v and acceleration g. So all distances must be proportional to v square over g. Hence the entire shape must scale as the velocity squared, which is answer D, 4 times height, 4 times width. That was answer D, and that was solution for problem number 13. Problem number 14. A ball is launched at speed v at angle theta above the horizontal toward the vertical wall a distance L away. It bounces elastically off the wall and falls back to its launch point. What was its initial speed? Solution for problem number 14. The range formula for ball is total distance, which is 2L equal v square over g multiplied by sine 2 theta. And from here we can find that speed equal this expression, which is answer E. That was a solution for problem number 14. Problem number 15. A mass M equal 100 gram is attached to the end of a string of length R equal 2 meters. A person swings the mass overhead such that their hand travels a circle of radius small r equal 3 centimeters at angular velocity omega equal 10 radians per second ahead of the mass m by an angle of pi over 2. Estimate the force of our resistance on the object. Solution for problem number 15. Let's draw a free body diagram for this process. On this picture we have tension in the string T, create angle between string and the big radius theta. It means that this tension in this direction must be compensated by force of higher resistance, and we can count it. We have tension equal m omega square big R, and we have projection of tension in body motion equal tension multiplied by sine theta, which is approximately T small r over big R, which is m omega square small r. And after putting numbers we have 0.3 newtons. That's answer D, and that was solution for problem number 15. Problems 16 and 17. The following information applies to problems 16 and 17. A hoop of radius small r is launched to the right at initial speed v0 at the ground level. As it is launched, it is also spun counterclockwise at angular velocity 3v0 over r. The coefficient of kinetic friction between the ground and the hoop is mu k. Problem number 16. How long does it take the hoop to return to its starting position? Solution for problem number 16. When the hoop is moving, it is slipping, and because initial speed was v0 to the right, and if the hoop is slipping till it will return to initial position, its velocity will be v0 to the left. It means that total change of velocity will be 2v0. And in that case, because acceleration due to force of friction is mu kg to the left, and the total time must be equal to delta v over a, which is 2v0 over mu kg. That could happen if our hoop is moving and slipping till it will reach the initial point. Now we need to count what will be angular velocity when it will return to the initial position. For rotation we have equation I alpha equal mu k m g r, where I is moment of inertia, alpha is angular acceleration, mu k m g is force of friction, and r is radius. So it means that on the right we have torque. Now we can count what is angular acceleration. For hoop we have moment of inertia I equal m r square, and we have angular acceleration alpha equal mu kg over r. So it means that total change of angular velocity equal alpha t, and after putting all these expressions we have 2v0 over r. It means that the final angular velocity will be initial angular velocity minus delta omega, which is v0 over r, and this correspondent with the velocity of this hoop to the left. It means that exactly in this initial position it will stop to sleep. It means that we counted total time 2v0 over mil kg correctly. And that was answer B. And that was solution for problem number 16. Problem number 17. Would the answer to the previous question, namely the amount of time to return to the starting position, be the same for the uniform disk with the same coefficient of friction, launched with the same initial conditions? Solution for problem number 17. Because for uniform disk we have moment of inertia I is 1/2 mr square, which is twice less than for hoop. We have angular acceleration is twice greater than for the hoop. It means that our disk will start to move without sleeping earlier than for hoop. It means that it will spend more time to return to initial position. Correct answer is D. No, because the disk stops sleeping too soon. That was a solution for problem number 17. Problem number 18. Uncertainty in the time for a car to complete a race. The car begins with an initial speed v0 and maintains a constant acceleration a throughout the race. Both v0 and a have independent uncertainties of 10%. Which contributes greater uncertainty to your estimate of the time for a car to complete the race? Solution for problem number 18. If we have initial velocity, acceleration and full distance, we can find the total time using quadratic equation. At squared plus 2v0t minus 2d equals 0. The positive root for this equation is this one. Let's estimate this solution for small distance and for big distance. For small distance we have this approximation, which is about d over v0. And we can see that for small distance time has dependent only from distance. It means that the main contribution was from uncertainty of distance. For big distance we have another estimation, which is this one. We see that this time mostly depends from acceleration, and we have only contribution for uncertainty for acceleration. It means that correct answer is A. And this was a solution for problem number 19. Problem number 19. A physical pendulum consists of a mass on one end of a massless rigid rod that can pivot about the opposite end, assuming the oscillations have an amplitude of 90 degrees. Which of the following graphs best shows the total acceleration of the mass as a function of the angular position theta measured between the pendulum and the vertical direction? Solution for problem number 19. Let's count what is the acceleration in any point with the angle theta to vertical. The acceleration could be split by tangential and normal acceleration. Tangential equal g sine theta, and normal could be found from energy conservation, because normal acceleration equal v square over L, where L is length of pendulum and v is the speed, and v square equal 2gl multiplied by 1 minus cosine theta. So we have normal acceleration equal 2g multiplied by 1 minus cosine theta. And now we can count what is total acceleration. The total acceleration square equal tangential acceleration square plus normal acceleration square, which is g square multiplied by 1 plus 3 cosine square theta. Now let's analyze this expression. In highest point where theta equal 90 degrees, cosine equals 0, and means that acceleration equal g, which could be for graph A, for graph B, and for graph E. For angle 0 degrees, cosine equal 1, and the acceleration equal 2g, which is 20. And we have only graph A, which is corresponding to this behavior, and also graph A corresponding to function which is decreasing from 0 to 90 degrees, which is a function we wrote here. So it means that correct answer is A, and that was a solution for problem number 19. Problem number 20. A block on a ramp is given an initial velocity v0 upward along the ramp. It slides upward for a time tu, traveling some distance, and then slides down for a time td until it returns to its original position. What is td in terms of tu? The height of the incline is 0.6 times its length, and the coefficient of kinetic friction between the block and the incline is 0.5. Solution for problem number 20. Let's write equation for distance as a function of acceleration and time. That's equal to 1/2 acceleration up multiplied by time up squared, which is the same as 1/2 acceleration down multiplied by time down square. And from this relation we can find that relation between times equal to opposite relation from square root of accelerations. Let's count accelerations up and down. Acceleration up equal g sine theta plus mu g cosine theta. Acceleration down equal g sine theta minus mu g cosine theta. So it means that time down over time up equal square root from acceleration up over acceleration down, and after putting all numbers we have square root from 5, which is answer C. That was a solution for problem number 20. Problem 21. An empty freight car on a level railroad track has a mass big M. A chute above the freight car opens and the grain falls down into the cart at a rate of R, measured in kilograms per second. The grain falls a vertical distance h before hitting the bed of the freight car without bouncing up. How much normal force is exerted on the freight car from the rails at a time t after the grain begins to hit the bed of the car? Assume the grain starts from rest. Solution for problem number 21. The upward normal force on the freight car must equal the total downward force experienced by the freight car. The freight car experienced 3 downward forces. First, the freight car's own weight, which is big mg. Second, the weight of the grain accumulating in the freight car. The grain accumulates at a mass rate r, so after a time t, the car contains a total grain mass rt. Thus, the total weight of the grain after time t is rtg. And third, the force from absorbing the momentum of the falling grain when the grain lands on the cart. Over some time interval delta t, an amount of grain with mass delta m equal r delta t falls onto the cart. The grain falls from a height h, so it lands on the cart with a speed v equal square root from 2gh. Thus, the grain carries a momentum delta p equal delta mv or r delta tv. And finally, the rate at which the momentum is delivered to the cart, or the force experienced by the cart, is delta p over delta t, which is r multiplied by square root from 2gh. Thus, the normal force, which equals the total downward force on the cart, is this one, which is answer E, and that was solution for problem number 21. Problem number 22. The bruise threshold for a fruit is the largest height it can be dropped from rest without bruising. The bruise threshold of a 0.2 kg apple on steel is 10 centimeters. Suppose that it always takes 0.1 seconds after impact for the apple to fully stop, and that 4 centimeters square of the apple comes into contact with the surface during the impact. What minimum average pressure is required to cause the apple to bruise? Solution for problem number 22. Solution for problem number 22. To find what is minimum average pressure required, we need to find what is the average force, because pressure equals force over area of impact. To find what is the average force, we have to find what is change of momentum, which we can find from formula impulse Ft equal change of momentum mv. Now we have to find what is speed when this apple touched the ground. That will be square root from 2gh. And finally we have this expression, which is after putting numbers we have 7100 pascals, which is answer C, and that was solution for problem number 22. Problem number 23. A train travels at 360 km per hour on an almost straight track. The track is slightly sinusoidal with a vertical amplitude of h over 1 km distance, as shown in a figure. If the maximum tolerable vertical acceleration of the train is set at 0.1 meters per second square, what is the maximum allowable size of h? Solution for problem number 23. Because this path is sinusoidal, we can write equation for vertical motion. That will be y equal h multiplied by sine omega t. From here we can find what is vertical acceleration. That will be negative omega square h sine omega t. And the maximum acceleration will be omega square h. And from here we can find what is maximum height. To find what is omega, we have to find what is the total period, which is time to travel this train for 1 kilometer. That will be omega equal 2 pi over t, and t equal distance over speed. Speed we have to translate to meters per second, which is 100. So we have total time or period equal 10 seconds. It means that omega equal 0.628 or height equal maximum acceleration over omega square, which is 0.25 meters or 25 centimeters, which is answer B, and that was solution for problem number 23. Problem number 24. A uniform rope of length L and mass M passes over a frictionless pulley and hangs with both ends at equal heights. If one end is pulled down a distance x and the rope is released, the acceleration of that end at this instant will be next one. Solution for problem number 24. This problem identical to problem with a pulley and two masses M1 and M2 connected to both ends of this rope. M1 equal this expression and the M2 equal this expression. So it means that acceleration equal M2 minus M1 over M2 plus M1 g, which is 2x over L g. That was answer E, and that was solution for problem number 24. Problem number 25. A student makes an estimate of the acceleration due to gravity g by dropping a rope from a known height h and measuring the time t it takes to hit the ground. Neglecting a resistance, which one of the following situations will lead to the smallest value of the relative uncertainty dg over g in the estimate? Solution for problem number 25. Let's write equation how is height depend from acceleration due to gravity and the time. We have height h equal 1/2 gt square, and from here we can find what is the acceleration g. That will be 2h over t square. Now we can find what is total uncertainty if we know independent uncertainties for height and for time. That will be this formula. Here dg over dh, that's a partial derivative from this expression, and we have this expression. And now we have to divide this equation by initial equation squared, which will give us this expression. And now let's use this expression to examine what happened in all cases. Suppose that we have first case A. There is no uncertainty in t, and the h has uncertainty 10%. So it means that in this equation we don't have this member, and if we have 10% for h, we have 10% for g. So in case A we have uncertainty 10%. Now let's do case B. There is no uncertainty in h, and t has uncertainty 10%. If we look at this formula, this is 0, and for uncertainty 10% in delta t, we have total uncertainty for dg over g will be 20%. Now let's examine C. Both have uncertainty 5%. If we put it here, in case C we have uncertainty 11.2%. So it means that minimum uncertainty, we have a minimum relative uncertainty in case A and maximum in case B. So it means that the correct answer is A. That was solution for problem number 25.